Okay, good evening everyone and welcome to the 11th session of the course Measure and Integration. So today I'll start with some question that I left in the last session and then I'll go on the theory part. So today I'll be mainly discussing more properties of LP spaces and then I'll define what convolution is. Okay, so let's start today's session. Let us start with this problem. So I think there is a theorem in the book itself and you must have seen in the lecture something similar to this. Okay, so here what I'm saying that if f is in, and the proof will be similar to what you have seen there. Okay, so it's sort of a repetition of what you have seen. Okay, so here the thing is that if the function f is in LP for some p finite, okay, and it's in L infinity, so you already know that. So let's say this is p and okay, infinity is like at infinity. So you already know that if a function is in p and q, then it is in the all in between spaces, right? So now since f is in LP and f is in L infinity, so let me start with the solution. So since f belong to LP and f belong to L infinity, this implies that f belong to LQ for all q which are lying in between, right? So for all q belonging to p infinity. Okay, so what does it say? That this function f will belong to LP spaces after certain thing. Okay, so here it's q, so it will belong to LQ spaces for q greater than p. And the reason, because of this, that f belong to LQ for all q in p comma infinity, we can talk of this norm for large q. Okay, and that is why we can talk of this limit. Okay, so we still don't know that whether the limit will exist or not, but the first thing what we need to make sure that this LQ norm should be finite. This is what we are concerned with. This should be finite. Now since we are dealing with this q tending to infinity, okay, so for that reason we need q, this norm, to make sense for large q, right? Because we are studying the limiting behavior. So that is why this is enough for us for this problem to make sense. Okay, so that's why we just started with f in LP intersection L infinity. That gives sense to this problem. Okay, so now you have this, that f belong to LQ for all q greater than p. Okay, so we are dealing in some omega set. Okay, so I am not writing it, but if you want you can write it somewhere that we are in omega, some open subset of Rn. Okay, so everything is in LP omega, L infinity omega, so and so on. Okay, so this makes sense. Now we have to make sure that the limit exists and the limit of LQ norm of f will converge to L infinity norm of f, right? I have said similar sort of thing in the last session. Okay, so now I will be proving this. Okay, so so you already know this type of estimate. What I was saying, that if f belong to LP, f belong to LQ, then you know that f belong to in between spaces and the norm is, so let me recall this thing somewhere. So suppose this is R which is in between P and Q, so you know that f of R is less than equal to f of R is less than equal to f of infinity and f of P, but there will be some power, right? So here you can, it's theta, so you can write theta and 1 minus theta sort of thing. Okay, and this theta you can determine by this P and Q. Okay, so when P and Q are given, you can determine this theta, right? So this sort of thing we have already seen. Okay, and in this case it will be basically, so how should I say, here this theta can be find out. So what will be the theta? Okay, okay, you can see it, but this theta can be found, we can determine this theta in terms of P and Q, okay, in general. So here it's say it's Q, then we can determine theta can be determined using P and Q, okay, in terms of P and Q. Okay, So we have this type of estimate, right? So here similarly norm of f of q will be less than equal to, so norm of f infinity raised to the power, okay, so in this case this theta will be 1, okay, so this will be f infinity and f raised to the power p, and then I think it will be 1, it will be 0, right? Something like this. Just a second. If okay, let us find, if you want we can find it. So norm of fq is equal to mod fq, okay, and you want f to be in lp, so you want basically mod f p, and then you want mod f, so you will be mod f q minus p, right? Now you can take this in infinity norm, so norm of f p q minus p, okay, just right, so q minus p infinity norm, and you will have, okay, just a second, so you will have 1 by q, so 1 by q will be here, okay, and you want here to be p, yeah, so just a second, I'll have to do a bit of manipulation. So what you can do is, you want here p, okay, and here you want 1 by p, so you do p by q, 1 by p and p by q, right? Okay, and then you can take this L infinity norm, so you can take L infinity norm of q minus p outside, and then you have mod fp and whole raised to the power 1 by p by q, right? So now you can rewrite this as, so you'll have here norm f infinity p by q, if you take, so p by q, q minus p, and norm fp p by q, right? So yeah, so the formula would be like this, right? So norm of, so what I am doing here, just let me tell you. So norm of fq, you know that the by definition it's mod f raised to the power q, and then you take 1 by q. Now what I am doing, now I know that f is in lp and f is in L infinity, so that is why what I am trying to make, I want to make norm of fp on the right hand side, so that's why I write f raised to the power p separately and q minus p, right? Now I want to bring 1 by p in the bracket, so I'm in the power, so instead of 1 by q I'm writing 1 by p times p by q, okay, so this is nothing but 1 by q only, okay. Now what I'm doing, I'm taking L infinity norm of this one outside, okay, so you know mod of fx is less than equal to L infinity norm, right? So I'm using that result, so here I will have norm f infinity q minus p outside, and this will be as it is, so integration over omega or whatever it is, so here it integration over omega of mod f raised to the power p, right? Now in the numerator, in the power we have 1 by p by q. Now what I'm doing, I am just this simply I'm putting the power on both the component, so here it will be p by q minus p, and here it's lp norm and raised to the power p by q. So you can also simplify further to get f infinity, and then you have p, q will be cancelled, 1 minus p by q, and here you will have f p by q, okay. So I hope this is clear. Do you have any doubt here? I hope this is fine. I don't know. Is this fine, or you are facing any problem? I think this p should not be there somehow, because it's theta and 1 minus theta should come. I don't know. I think here there is some problem. Okay, I mean whatever, but the main point is that you can estimate this q norm with the L infinity norm and p norm, okay. I'll have to check why this p is coming here. So q minus p and then 1 by p. Oh, why p is coming? It's not there, right? So this p cancels. So 1 by q will be 1 minus p by q, right? Okay, it's fine. Okay, so this is what I'm getting. So I'll just write norm of fq is f infinity 1 minus p by q, and here it's p by q, right? This is the estimate, and I have derived it here. I think in the last session I missed this part somehow. I didn't prove this part. Okay. So this is the estimate that we have on this norm. Now you can take Lehm soup, right? So this is less than equal to this, right? Now you can take Lehm soup on this one, norm of fq, right? Okay, so now let's take Lehm soup of q tending to infinity, norm of fq is less than equal to, now as q goes to infinity, this, notice this quantity, so this will go to 0, so this will converge to 1, right? So what you have is norm of f infinity, and this will converge to 1 as well, so this will again go to 0, so you'll have only 1, so this will be 1, right? So only this quantity will be left. Okay, so this is one of the inequality what we have got so far. Now let's look for the other way around. Okay, so now what you do, so this was one part. Now, so for epsilon belonging to 0 comma norm f infinity. Okay, so you know that this is finite, so we are taking epsilon in between 0 and norm f infinity. Okay, so now consider this set a epsilon given by x in x such that mod of fx is greater than norm of f infinity minus epsilon. Now notice that epsilon is less than this, so this is greater than 0. I mean, that's just a remark. So this is greater than 0. Okay, so this is the set where we are what we are considering. So it's saying that now this this measure of this set will be non-zero, right? By the definition of f infinity norm. Okay, so we know that f is almost, I mean, for all points, almost all points, we know that this holds, right? So now this is the infimum. So if you recall the definition, this is the infimum of m greater than 0 such that mu of mod f greater than m is 0, right? So now by the property of infimum, I can say that this measure of this set, okay, so m or mu if you want, so mu or, okay, let me write mn only, so mn of mn of this set a epsilon will be greater than 0, and that is just because of the definition, because you are making this less than, this is the less than infimum, so such x, so this set will have measure, positive measure, right? This is just by the property that this is the infimum, I mean just by the definition. So the reason being this one. Okay, so this is the reason by definition. Okay. Okay, so now this measure has, I mean the measure of this set is positive. Okay, now you consider this integral mod of f raised to the power k dmn. Okay, here I was writing. Okay, so I have not mentioned the measure, but okay, you can deal with this Lebesgue measure, because the Lebesgue space is defined for the Lebesgue measure, right? Okay, so now you have this. Now you know that this is over the whole x. Okay, now this is the bigger set x1 x, so I am restricting this integral to this set a epsilon. So I am restricting this to a epsilon mod fq d of mn. Okay, so now over this I know that this function is greater than equal to f infinity minus epsilon. So what I can do is I can write this is greater than equal to norm of f infinity minus epsilon, and then I'll have this measure of a epsilon, right? Okay, so I have this now. So what I have got, that norm of fq is greater than equal to norm of f infinity minus epsilon raised to the power 1 by q, and mn of a epsilon raised to the power 1 by q. Right, so I am taking 1 by q power on both the sides, so I am getting this thing. Now I will take lim inf q goes to infinity, right? So now if I take lim inf, okay, just a second, so here it will be q, right? So if you want, let me write it here. So you know that this is a epsilon, and this is this function f of this function is greater than equal to norm of f infinity minus epsilon mod, or okay, since this is positive I am writing q. Okay, so this q will come, so I mean 1 by q will not come. So when I take the power 1 by q in both the sides, so this 1 by q will not be there. Okay, so now when I take lim inf norm fq as q goes to infinity, it will be greater than equal to, so now as q goes to infinity, this will go to 0, so this whole quantity will be 1. So what I have is norm of f infinity minus epsilon, right? Now this epsilon was chosen arbitrary, so it can be very small, right? So since this epsilon can be very small, as much as you want you can make it, so that's why this implies lim inf q going to infinity norm fq is greater than equal to norm f infinity, and the reason being, since epsilon greater than 0 belonging to 0 comma norm f infinity is arbitrary small, I mean it can be made arbitrary very small. Okay, so we have got the another desired inequality, right? So you had got that this lim sup is less than equal to norm f infinity, and you have also got that lim inf is greater than equal to norm f infinity. So I mean just using, so let me combine 1 and 2 if you want. So if you combine 1 and 2, what you get is norm f infinity is less than equal to lim inf norm fq, and you know that lim inf is less than equal to lim sup, so it's lim sup norm fq, and by 1 you know that this is less than equal to norm f infinity, right? So as q goes to infinity, as q go to infinity, right? So since this and this are same, so this equality should hold in this whole inequality. So you'll have this implies lim inf of norm fq is equal to lim sup of norm fq, and this is equal to norm f infinity, and hence since lim sup and lim inf are equal, so limit exists and the limit would be equal to this lim sup value. So therefore limit norm fq is equal to norm f infinity. Okay, so do you have any doubts so far? Is everything fine?
Yes, sir.
Okay, so now let's move to the next problem. Okay, and this problem is somehow related to the third one. Okay, so let's see what this problem is. So suppose you have this pqr, and notice that all these are strictly less than infinity, so none of them is infinity, and assume that this pqr satisfies this property that 1 by r is sum of 1 by p and 1 by q. Okay, now the question is that if your f is in LP, so from here actually you can guess, right, that 1 by r is greater than 1 by p and 1 by q, right? Because when you are adding this you are getting 1 by r, so 1 by r is anyway larger. Okay, so it says that if f belong to LP and g belong to LQ, then the product belong to LR. Okay, and this sort of thing is true, that int mod fg is less than equal to, or sorry, norm fg is less than equal to norm of f and norm of g. Okay, so I'll just tell you one specific case of this at first. Okay, so let me write one particular case of this. Okay, what you generally you will use. Okay, so see, so take p to be 1, p to be 2, q to be 2, then from this identity, for this identity to be true you have to take r to be 1. So this imply r equal to 1, right? Okay, if you don't want, so let r equal to 1, then this satisfy 1 by p plus 1 by q equal to 1 by r. Okay, so you understood that this holds. Now this theorem is saying that if so it's better directly to write this inequality. I mean, I don't want to write all this. So what this inequality says, that norm of fg 1 norm is less than equal to norm f2 norm g2. Okay, so in other words, this says that this mod fg, right? So this is the norm 1, right? That mod of fg integral is less than equal to this L2 norm of f and L2 norm of g. Now, I mean, the thing what has been written here is just implication of this inequality. That suppose f is in L2, that means that this is finite, right? F in L2 means this is finite. G in L2 means this is finite. Then that would imply that fg is in L1, right? So that's it. So this was one particular case. What I feel that when you will do your research work, I think this would be more helpful. I mean, it will come again and again. So this is used in finding the and doing the estimates and all. So okay, so this is just one case of this. But more generally, we have this one, that if 1 by p plus 1 by q is 1 by r, then the product fg will belong to LR if f belong to LP and g belong to LQ. Okay, and the LR norm of fg will be estimated in this way. Okay, so now I think I have said much, so let's go to the proof. Okay, so we have to, so as I mentioned here, that the main thing is to prove this inequality. Once you prove this inequality, this is coming just from this one. So what it says, that f belong to LP means that this is finite, g belong to LQ means this is finite, and since this and this is finite, this has to be finite, and this would mean that fg belong to LR. Okay, so our main goal would be to prove this inequality. That's it. Okay, so I'll be proving this inequality. So let's see. So you have to estimate fg LR norm, right? So what is, I mean, by the definition, what we mean is this mod fgr and then 1 by r. So this is just by the definition. So let us see what this integral is. So let us look at this integral mod fgr. And again, as I did some manipulation here, like while I was proving this estimate, in general you have to do this only. What you know, what you want, using that you have to prove something. Okay, so as I want here this LP norm of f on the right hand side and LQ norm of g on the right hand side, I'll try to use this one. I'll try to bring them. Okay, so see, this is nothing but mod f r and g of r, right? So I want LP norm of f. So what I'll do mod f p. Okay, and so since we have r, so I'll have, so p by r and then r. Here I'll have g by q. Okay, and then I'll have, sorry, I mean it should be p, right? It's p r by p, and here q r by q, right? So just because I want LP norm of p. Okay, now I'll use this this inequality, Holder's inequality, right? So I mean this is actually the Holder's inequality, right? This one, this is coming from Holder's inequality as well. Okay, I mean, so here, so what I can do now, notice this fact here, so I'll just write it here. Notice this term, just mod f raised to the power p. Okay, so let me define f1 to be mod f raised to the power p. Now can you tell me where it belongs? See, if you notice, if I take this f1 raised to the power p by r, p by r or r by p, just a second. if I write f1p, yeah, my claim is that this belong to L of p by r. Why? Because if I do f1 p by r, so this is mod f, no, r by p, just a second. No, p by r only, just a second. F1 p by r would be f, okay, I am taking f to be wrong, I mean f1. I should deal with f1, this whole p to the power.
Sir, F1 is equal to mod of F to the power R. It is belongs to the P
F
by
to the
R
power,
integral.
no, r, okay, you are saying mod f raised to power, so this will belong to L of
P by R.
p by r, right? I think so, yeah. So just let me take, so mod f1 raised to the power p by r would be, right, mod f raised to the power r, p, and we know that this is finite because f is in LP, right? Yeah, thanks. So if you take f1 to be mod f raised to the power r, so okay, so I think we can directly deal here itself, right? So let us deal directly with this one only. I mean the guess was from this one, okay, so the guess is coming from here, and because here you can see that this r by p is coming, so I will take p by r, I mean reverse of that, so that this mod f raised to the power p would come, okay. So now I will simply use this Holder's inequality. So what I get is mod, so I know this f1, so let me write it in bracket. So now I know this f1 is in LP by r, and this g, similarly you can show that g1 equal to mod g raised to the power r will belong to L of q by r, right? And this so this 1 by p by r plus 1 by q by r, if you see, this would be r by p plus r by q, and this is nothing but r times 1 by p plus 1 by q is 1 by r, this is 1 by r, so this is 1, so they are conjugate exponent, right? So now I can use Young's inequality, okay. So this was first thing, second thing, and the third thing is this one. So now I am eligible to use this Young's inequality. So now from Young's inequality I can write this mod f1, so let me say this is f1, this is g1, so I can write mod f1, so this I can write is norm of f1 LP by r and norm g LQ by r, right? And now I know that norm f LP by r norm would be, so this would be mod f raised to the power p whole raised to the power r by p, right? And here it will be norm g raised to the power q raised to the power r by q. So now this would be norm f p raised to the power r, and here it would be norm g q raised to the power r, right? So this is what we got, okay. So now I'll take 1 by r both side, so I'll get norm fg LR norm is less than equal to norm of f pr norm of g q, sorry, this r will not be there. So this is what I got, right? So this is what we wanted, this type of estimate. So here also we are doing nothing, just a bit of manipulation, and so the main thing what we are using here is this Holder's inequality, okay. So here I should mention that this is by Holder's inequality. Okay, and this whatever I said, I think it follows from Holder's inequality as well. This is a particular case of Holder's inequality, I mean this one, okay. Okay, so now this problem is somewhere application of the last one what I did. So let me mention this estimate first. Let me just copy this one. So put it here. Okay, so what is given there? Again, the same sort of condition that you have PQR lying between 1 and infinity, and PQ satisfies this type of identity. Then the question is that if Fn is converging in LP and Gn is converging in LQ, then you have to show that Fn Gn converge to Fg in LR. Okay, so what we have to show? So to show that Fn Gn minus okay, so yeah, I can write this. So Fn Gn converging to Fg implies Fn Gn minus Fg LR norm goes to 0 as n goes to infinity. This is what we mean by convergence in LP spaces, right? So LP norm of Fn minus F should go to 0. Okay, so this is what we need to show. Okay, so let us try to estimate this one. So norm of Fn Gn minus Fg LR norm. Okay, so I'll use triangle inequality. So what I have is, so I'll just add Fng and I'll add Fng and subtract Fng. So I'll have Fngn minus Fng, and then I'll add Fng minus Fg, right? So this is R norm. Now I'll use Minkowski's inequality to write this Fn. So from these two terms, if you see, from these two I'll take Fn common, and from these two terms I'll take G common, right? So I'll have Fn minus F here, and here I'll have Gn minus G. So this is Fn Gn minus G. So I'm using Minkowski. So this will be R plus norm Fn minus F and then times G LR norm. Okay, now I'll use this star. Okay, so when I'll get here Fn raised to the power P and norm Gn minus G raised to the power R, Q, and here I'll have norm Fn minus F P norm G R, right? Now you know. Okay, so you have seen this type of thing in real analysis as well, that if a sequence xn is convergent, imply that mod xn is bounded, right? So xn convergent implies xn is bounded. That means mod of xn less than equal to m. Okay, in a similar way, so similar to this, you have this as well. So you can prove this, that since Fn converges to F, and the proof will be similar to what you have seen here, Fn converges to F in LP would mean that this sequence of Fn is bounded in LP. Okay, and bounded in LP means that norm of F, so there exists some m greater than 0 such that norm of Fn, P norm, will be bounded by m. So this is we have. So since you have seen that, this is in our assumption that Fn is converging to some function f in LP norm, and that is why this will be bounded. Okay, so this is bounded. Okay, so here you can ignore this n term. N does not matter. This G is in LR because, okay, so this also you know that Gn converges to G in LQ would mean, okay, sorry, this should be Q. Okay, so now you know that this Gn converges to G in LQ. That means this G is in LQ as well. Okay, so this G is in LQ means that this is also finite. This is just a constant thing, right? Okay, now when you pass the limit as n goes to infinity, Since Gn converges to G in LQ, this will go to 0. Fn converges to F in LP would mean that this goes to 0. So overall, now since the right hand side goes to 0 and on the left hand side this is norm, so this is always greater than equal to 0. So you can conclude, so limit of norm Fn G Gn minus f of G LR norm as n goes to infinity is 0. Okay, so this follows from here, and this is what you were required to prove, that this Fn converges to Fg in LR norm, right? So this is just an application of what we have proved in the last problem. Okay, so is this fine?
Yes.
Okay, so now we can move to the theory part. Okay, so today we'll be mostly talking about this approximation result. What I hope you must have seen these results earlier. So I'll just state the results. Okay, so to start off with, let us assume that this omega is some non-empty subset of Rn. Okay, and this S is a collection of the simple functions. Okay, so this is collection of this simple function defined on omega. Okay, but the main thing is that it vanishes outside the finite Lebesgue measure. So what it means, that suppose you have this simple function looks like this, right? Phi alpha I chi of ei, where so you can assume that ei's are disjoint. So you can assume ei are disjoint. Okay, now what it says, so suppose you choose any element x from here, this will, if x belong to ei, the function will take the value alpha I, right? Now what it says, that it should vanish, and okay, also you can assume that alpha is non-zero, right? Because if alpha is 0, we will not count that ei in this set, right? So we can assume that alpha is non-zero. Now it says that it should vanish outside the set of finite Lebesgue measure. That means the place where it is non-zero, it should be finite. I mean, the set over which it is non-zero, it should be finite. Here you see that this simply means that these ei's, whatever ei's are coming in this expression of this phi, should be of finite Lebesgue measure. Okay, so this simply means that the Lebesgue measure of this set ei is finite. Is this clear what I just said? Yeah? Do you have doubt?
Yes, sir.
Okay, so you have seen this is what we mean by this set S. Okay, so S is defined in this way. Now the next thing what I'm saying, that a simple function will be in LP if and only if phi belong to S. Okay, so I shall give, I mean it's quite easy, but okay, I can prove it if you want. So should I prove it or is it clear to you? I mean, if it's clear, then I can just leave this. Are you comfortable with this remark?
Sir, can you explain?
Okay, so so what my claim is, that phi belong to LP. So let me prove this way. Phi belong to LP imply phi belong to S, and the other one would be that phi belong to S implies phi belong to LP. Okay, so omega and omega is there. Okay, so phi belong to LP implies phi belong to S. So suppose by contradiction, so assume phi does not belong to S. Okay, now what will that mean? This would mean that there exists some k or some I, right, in this expression, such that mn of ei is infinity. right? This is, I mean, if it does not belong to S, this would be the the contrapositive of this statement of S. I mean, the way this S has been defined, or negation of that thing, right? So this is the negation of what I just explained. So there will exist some I for which whose measure is infinity. The moment I say this measure is infinity, now look at this thing. So mod of phi, so of p over x, or omega, sorry. Okay. Now this omega is the, I mean, the main set, and these ei's are subset of that. So I can write this over ei phi of p, right? And now this phi is taking the value alpha I over this ei. So I can write this alpha I raised to the power p, and then I'll have this mn of ei, right? Now you know that this is infinity, so this is infinity. This implies that phi is not in LP, which is a contradiction, right? Okay, so phi is in LP, and this is just obvious that phi belong to S means what? That measure of each of the set is finite, right? So it's just a constant. So okay, if you want, I can write. So you can try this simply. You can calculate this phi of p. So it would be nothing but summation of, so this omega I can break it up. So from I equal to 1 to n, let's say. Okay, so if this is a simple function, so now I'll have this alpha I and mn of ei. So alpha I raised to the power p and mn of ei. And now you know that each of this measure is finite. This alpha I is a real number and everything is finite, so this is finite. So this implies that phi LP norm is finite, so phi belong to LP. Okay, so this is, I mean, this is just standard thing. So this is what I was saying, that phi belong to LP would mean that this is possible if and only if this phi is in this set S. Okay, and okay, so I mean, that's it. Okay, now now let us look at this lemma. So it says that suppose you have a non-empty open set and p is lying between 1 and infinity. So p is not infinity here, okay? Then any function f, okay, so any function f in LP. So I think it should be written here. So if you want, you can add it here. So any f in LP. So if you take any LP function, okay, that can be approximated by step functions. Okay, so see, if f is simple function, then you already know that LP, the simple function is in LP if and only if phi is in S. Okay, so but okay, let me mention one thing, that this step function and simple function, how are they different? So you know that the simple function is of this form, that summation alpha I chi of ei, where ei is any measurable set. So ei is measurable subset of, I mean, measurable set in Rn, right? But when you talk about this step function, okay, so phi is again of this form, alpha I chi of ei, but now the difference would be that ei's are the elementary set. That means if you are taking in R, it would be simply open sets or closed interval, sorry, set not open, interval or closed interval, or half open half closed interval, like that. So ei would be elementary set here. Okay, so that's the only difference. You can clearly see that every step function is a simple function. Okay, so you are just restricting this ei to be of a particular type, that's it. So this is what we mean by step function. So this lemma is saying that if you take any LP function, okay, you can approximate it using step function. Now what does the approximation mean? That if you have this f, there will exist a sequence fn, or if you want phi n. So approximation means that there exists a sequence phi n. So these phi n's are simple function. Okay, so phi n not simple, step function such that, so this phi n will converge to this f in LP such that this phi n minus f LP norm goes to 0 as n goes to infinity. So this is what we mean by this approximation thing. Okay, so we have a LP function, but we can approximate it using step functions in LP space. Okay. Okay, so now let's come to the main theorem. Yeah.
So when we are taking a step function,
Yeah.
and for any elementary set, then f is in LP, but LP space is the set of measurable function. Then the step function need not to be a measurable function.
No, these step functions are measurable by definition, right? So step function, as I've said, you remember that. Huh?
EI with any arbitrary set.
EIs, no, EIs are elementary set and these are measurable. So simple function by definition they are measurable. Okay, and I mean it will be in LP just because we are talking about elementary set. So this elementary set will be, if you are in R, it would be set like AB or AB. Okay, so this type of set, or maybe AB in case of R. Okay, so the measure of this set will also be finite, so it will be in LP as well. Okay, by I mean what I have said here, and by this. Yeah, is this fine what I said?
Yes, sir.
Okay. Okay, so that's why we have written step function to be more precise, because if you just write simple function, then that need not be in LP, because the reason being that this EI's set, these EIs may have infinite measure, right, when we just talk about simple function. But we can also approximate by the functions containing in this S, that is simple function but with which are vanishing outside a set of finite Lebesgue measure. So instead of this step function, you can write that it can be approximated by functions of S as well. And anyway, I mean what I am saying here, or what this result is saying, is much more, I mean, is better one, because they are saying that you can, so you notice this step function is a subset of this S, right? So now when I'm saying that any function can be approximated by step function, that simply imply that it can be approximated by this S function as well. I mean, because step function are inside this. Okay. Okay, now is it fine, or do you have still some doubts?
Yes, sir.
Okay, so now let's come to this theorem. So this theorem says that suppose you are in LP space. I mean, okay, so in the consideration, this P is always finite here now. So P can be 1, but it is not infinity. Okay, so what it says, that this CC function, so CC function, okay, so do you know the support? What do you mean by support of a function? I think I must have mentioned it somewhere. So do you know the support?
Sir, closure of the set of the point where the function is non-zero.
Exactly, yeah. So closure of the set where the function is taking non-zero value. Okay, so you already know that. Okay, so it's fine. So now this CC function denote the space of continuous function. Okay, so it's a space of continuous real valued function defined on omega, whose support, so you know support is always closed because you are taking closure. Okay, but here you are saying that this CC means that the support should be compact. That means, so since we are dealing in Rn, we know that compact if and set is compact if and only if it is closed and bounded. So what it means, that CC functions are basically the function space of continuous function. So this bigger C stands for this continuity, I mean the space of continuous function, and this small c denotes that the support is compact. Okay, so that's the meaning of notation. Okay. So it says that CC infinity function is a space of continuous function with compact support. then you have this result that CC omega is dense in LP omega. Okay, so I mean dense, if you want to understand by norm, you can say that CC of omega, if you take closure of this set with respect to LP norm. Okay, so if you take closure of this set with respect to LP norm, you will get LP omega. Okay, so this is what it means by dense. Or if you want to understand in sequential term, which I think will be more useful for you, is this one, that dense means that if you take any f in LP, okay, then there exists a sequence Fn. You can always find a sequence Fn in CC. So Fn belonging to CCX, okay, such that this Fn converges to F in LP, or Fn minus F LP norm goes to 0 as n goes to infinity. So this is what it means. Okay, so this is statement. Okay, so this is the sequential meaning, and this is what density actually, what you already know from topology, and this is what it means. Okay, so now this result is not true when you go for p equal to infinity, and the reason being that when you take this CC omega, so this CC omega with, you complete with L infinity norm, what you get is C0 omega. Okay, and this C0 omega is the space of function which vanishes at, I mean, boundary. So in case of R, so suppose when you are talking about R, it simply means that the function which are vanishing as x, so f belong to C0 of omega, so where omega, let's say, subset of R, so f belong to C0 omega implies that f is continuous. So you can make it different only if f is continuous plus, okay, plus f of x goes to 0 as mod of x goes to infinity. That means as x goes to infinity and x goes to x goes to minus infinity, the function is going to 0. Okay, so this is what it means by this space C0. So when you take the closure of CC infinity function, it is becoming C0, right? And I mean, you can actually see this, visualize this. So suppose you have, I mean, what I mean that, so CC means basically what, that it is supported somewhere like this. Okay, so the function would be like this, I mean something here. So let's not talk about what is here, but in this region it is always 0, the function, and here it's something, right? So now even if you go, I mean if you enlarge this support also, it will be 0 outside something. So as x goes to infinity, you can see that this function will ultimately go to 0. I mean that's just the intuition, I mean, of this argument. This is not the proof, but this is just for your feeling that okay, this result would be true, and in fact this is true. So this is some sort of justification what I am trying to give. Okay, just vague thing. Okay, so this is what we have, that CC functions are dense in LP. In fact, you can also prove that CC infinity functions are dense in LP. Okay, and this CC infinity function you can similarly understand, this is very smaller than this space, right? So you can actually prove this also. So this requires, I guess, some partition of unity. You have to smoothen up the functions. So the proof is available. If you want, you can read it. So this is also a result. This says that if you have a LP function, you will get infinitely differentiable function with compact support which approximates, I mean a sequence will exist of infinitely differentiable function with compact support which converges to that LP function. Okay, so such results are also available. Okay, so now let's go to the separability of LP spaces. So I don't know whether you know the definition or not. So separable basically means that it should have a countable dense subset. Okay, I don't know, I have written. So X, if you have a topological space, so this is said to be separable if you have a countable set which is dense also. So dense means if you take the norm Okay. Okay, so I mean, okay, in general topological spaces you need not have norm. So basically the closure, I should not write with respect to norm, but it simply means that the closure, so I mean x is separable would mean that there exists a countable set, so it will be something like xn n equal to 1 to infinity, such that this xn is dense. So I mean this is a set which is dense in this whole x. Okay. Okay, so this is the definition of separable separable spaces. So in case of LP spaces we have norm, so we can this density simply means that you will have a sequence of function which will converge to that in that limit, I mean in that norm. Okay, so in this LP space, okay, is separable for p in 1 infinity. So L infinity is not separable, okay, but LP for p in the range closed 1 comma infinity is separable. That means there will exist a countable set, okay, which will be dense in this LP space. Okay, so that is the property of separability. Even I don't know if you know the Sobolev space, I mean this property holds in there also. Okay, so this separability property of LP spaces will come to reflexive property as well in, I think, in some other slides. Okay, so this was about separability, that you just need to remember that LP space is separable for p in 1 comma infinity where 1 is included, but L infinity is not separable. Okay. Okay, so now let's come to this. So using those density results, what I have proved, what I have mentioned above, so you can prove this theorem, Lucian's theorem. You can do the reverse also. You can prove this Lucian's theorem independently, and then you can go for the proof of that approximation result. Okay, so in this book actually this Lucian's theorem is proved using that approximation result. Okay, so let us see what this Lucian's theorem says. That suppose if you have a measurable set with finite measure, so let E be a measurable set of finite measure, and let F be a function, real valued function defined on this set E. Okay, then for this function there will exist a CC function, okay, such that this measure of the points where the functions are not equal can be made very small. Okay, so depending on the epsilon, so what epsilon you choose, so this phi is depending on some sense on epsilon, that what epsilon you choose, there will exist a phi epsilon in CC Rn such that the measure Mn of x in E such that phi epsilon x is not equal to fx, the measure of this set is less than epsilon. That means they are almost equal, right? So for almost equal means outside epsilon set they are equal, this phi epsilon function and fx. So the function f, the measurable function which is having finite measure, okay, that is some way equal, in some sense it is equal to this CC function. You can see, that there is some relation between the approximation. This is not exactly the approximation result, but it is saying that if you have a measurable function with finite measure, okay, so this function is defined on that. So when you go for this LP function, you know that, so this is also a result. Okay, let me not go there. So you can get a feeling that, okay, this is somewhere related to the approximation one. That here also we are saying that this measurable function, now since we are taking in this E is of finite measure, you can clearly get that f will be, okay, I should not say because f is not bounded, but I cannot say f belong to LP. No, I cannot say, but okay, any measurable function you can see, LP space is a particular type of measurable function, right? So LP functions are again measurable function with LP norm finite. So here it is saying that if you have a measurable function, this measurable function is almost, or I mean, you can find a CC function with which they are equal outside some very small set. Okay, so measurable function is almost equal to this CC function. Okay, so you can always get such functions. Okay, so that's this Lucian's theorem says, and in fact you can get that this phi L infinity norm is less than equal to the F L infinity norm. Okay, so this the phi what you will get will the L infinity norm will be less than equal to the F L infinity norm. Okay, so again this is another application of this density results. So this is called Hardy's inequality. So what it says that suppose you have a LP function, LP 0 infinity, and now you define this capital F of x which is average of this f. So this is called average. Okay, so you are integrating over 0 to x, and you are again, so this 1 by x is nothing but Lebesgue measure of this interval 0x, right? I mean the length of this interval. So that's why this is average, that you are integrating on a some interval and then you are dividing it by the measure of that interval or the length of that interval. So it says that if you have f in LP, okay, then this capital F which is average of this f is also in LP 0 infinity, and the LP norm of f, capital F, can be estimated as follows, that capital LP norm of capital F is less than equal to P by P minus 1 small f LP norm. Okay, so you notice that this P is not equal to 1, so this does not create any problem. So this result is true for P lying between 1 and infinity. So for P equal to 1, this is not true. Okay, so I mean this is the example which shows that this is not true, this inequality is not true, or this theorem is not true for P equal to 1. So let me just explain this example. So now this f of x is exponential of minus x is in L1, right? And I mean you can actually integrate this. So you know that e raised to the power minus x 0 infinity is equal to, so 1 or plus minus 1 something will be there, right? So in 0 infinity, so you can clearly see that this function is in L1. Okay, but this, let us see what this fx is. So fx is saying that it will be 1 by x integral of f over 0x. So now if you integrate, so I'll not integrate, so you can clearly see it's quite easy. So it's from 0 to x, so at 0 it will be 1 and at x it will be e raised to the power minus x, and this 1 by x will come here. Okay, now you say you clearly you can understand that this is not in L1 because of this x, right? This x will create a problem, and that I can, if you want I can prove it. So it's just, so you see this integral of mod fx. So for this fx to be in L1, we need to prove that this integral is finite, right, over 0 infinity, right? This is what, if this is finite, then we will say that fx is in L1, right? So fx you can clearly see that this is 1 minus e raised to the power minus x, and you will have x, so 0 infinity dx. Now now what you can do is see the above part. So you know that e raised to the power minus x is a decreasing function, right? So it will achieve its maximum, it will achieve its maximum at 0 point. Okay, so if you want, actually it's better because it will become 0. So let us dominate this by some constant c and infinity. Okay, so it will be 1 minus e raised to the power minus x by x dx. Now you know that this exponential is decreasing function e raised to the power minus x, so it will be greater than equal to e raised to the power, less than equal to e raised to the power minus c, right? And so minus of this would be greater than equal to minus of this, so you'll have 1 minus e raised to the power minus c. Now that I can take outside the integration, so it will be 1 minus e raised to the power minus c and c to infinity 1 by x d of x. Now you know that this, okay, so if you want you can take c to be 1, so if you want you can take c to be just 1, just to be, okay, now you know that this is infinity, I mean this is not integrable, so this is infinity, so this capital F is not in L1. Okay. So you can clearly see this 1 by x is creating a problem. Okay, so this Hardy's inequality is not true for p equal to 1. This is what this example shows. Okay, so since this, similar to this inequality, and for this function capital F, which is average of small f, we have similar sort of inequality in small LP spaces, right? So you know that, as I have explained this earlier, that LP space is nothing but LP with natural number and counting power set of n, and you have this counting measure, right? So this, okay, so in general, when we talk of LP spaces, we consider Lebesgue measure, okay, but when you define LP for abstract measure, so you can define using any measure mu. So when in particular, since we are dealing with this natural number, we take this mu to be counting measure, and with this measure you get LP space. This is small LP space, okay. But in general, when I say LP, whenever you will see, in generally this is used for, this is called Lebesgue space, and this is with respect to the Lebesgue measure, okay. So that's why this, this sort of thing has a separate name, small LP, okay. And you have already seen that some properties are also quite different, right? So you know that LP is contained in LQ, or this is inclusion, when P is greater than Q, if I am not wrong, right? So this is true when you are on sigma on this space. So when you have finite measure space, and for infinite measure space you cannot conclude, but in case of this is also infinite measure space, and here you have the reverse, that LQ is contained in LP when P is greater than Q. I have mentioned these properties in the last session. So such property we have. Okay, this is irrelevant here, but fine. So similar sort of Hardy inequality is also true for this small LP space, and this says that, so suppose you have x in LP, so this is analog to this f in LP, right? LP 0 infinity, what we chose earlier, and this is analog to, so not this one, this is analog to this f, okay. So this f of n in some sense is yn, okay. So when this x belong to LP, so let me just rub this off. So when this x, which is a sequence of real numbers, so this is a sequence in real number in R, okay. So x is in LP, then if you define the sequence y, which is average of this sequence xn, that you sum x1 x2 till xn and you divide by n, okay. So this yn is also in small LP, and you have this sort of estimate. Again, this is true for p in 1 comma infinity, okay. Okay, so now let us see what do we mean by translation of a function. So this is the definition, okay. So if you have a function f, this tau h of f at evaluated at x means that you are evaluating the function f at x minus h. So you are shifting a bit, that's it. So that is the translation function, and this translation function is actually converged to this f when h goes to 0, okay. And that, this is an LP space, but this is pointwise as well. You can see pointwise, right? So tau h of f at x is f of x minus h. Now when you take h goes to infinity, h goes to 0, and this will converge to f of x, right? At least when the function f is continuous, for example, you say, okay. So then you can take the limit here inside and you will get fx, okay. So this is in fact true in LP's case, that this tau h of f converges to this f in LP space, okay. So this tau h of f converges to f in LP. So this is when f is in LP. So when you start the function f which is in LP, then the translation of that function will converge to that function in LP space, okay. Okay, so is there any doubt so far? Okay, so now let's come to the dual of LP space. Okay, so now suppose you have a normed linear space X. Okay, so for that normed linear space you can define the dual. So if you remember, I mean, in linear algebra also you have seen such things. The dual you have defined for X, you define X prime. So that is in finite dimensional setup, and this is in infinite dimensional setup. Okay, so let us first see what the definition says. So suppose you have this normed linear space X, okay, and then we define this dual of X as a space of continuous linear functionals on X. Okay, so I don't know whether you know. So basically, continuous linear functionals means that, so f defined on X to R, okay, such that f is continuous. Okay, so this collection of such function is called X prime. Okay, and this is the dual of X. Okay, is this fine? And so here continuity basically, so okay, since we are dealing in, so actually this sort of thing, I don't know if you have seen the functional analysis course, you must have seen this type of thing, operator, that t from X, so X and Y, let's say they are normed linear space. So if you have t from X to Y, then t is continuous. So if and only if t of X is less than equal to c times norm of X, right? This type of thing you must have seen if you have seen in functional analysis course. Here what you have, since Y is R, okay, now this norm will be removed by mod. So this is equivalent, equivalent condition for continuity. Okay, so that's it. So that this is how we define the dual. So dual is nothing but the space of continuous linear functionals on X. Okay, so what we'll be doing, we'll be trying to find the dual of LP space. Okay, so now we know that LP space is a normed linear space. So we have a norm, and in fact it is Banach space, it is complete also. Okay, so we have that LP is normed linear space. So now we'll try to find the dual of that LP space. Okay, so let us see how to go to the dual. So suppose you have a measure space X as mu, okay, and let's say, so for defining the dual, let's start with p in 1 comma infinity. So p is taking 1 also and infinity also. So as I mentioned earlier, that p prime is the conjugate exponent, that means 1 by p plus 1 by p prime is equal to 1. So this is the case when p belong to 1 comma infinity. Okay, so for p equal to 1 in 1, p prime is infinity, and for p equal to infinity, p prime is 1. So this is how we define the conjugate exponent. Okay, fine. So so let us try to start with some LP prime function. So assume that this g is in LP prime. Okay, now we define this t of g. So t of g is an operator which is acting on this LP space and is going to R. Okay, and how it is going? In this way. So Tg of, when you take any function f from LP, it is doing in this way. So Tg of f is integral of fg. Okay, and this is for all f in LP. So Tg is, so what I have written here, so this f is nothing but Tg here. So this is an operator which is defined on X. So X you see LP. So as I mentioned that I want to find what is LP prime, the dual of LP. So that's why, so okay, so this is coming from something. Okay, so this is, so if you want to understand, so let's start with, so this is coming from basically from the Holder's inequality. Okay, so why we choose this G to be in LP prime, so it will be clear why we have chosen. So initially you start with LP prime, you define Tg in this fashion. Okay, so now you have to prove that for this Tg to be in LP prime, what you need to show, that this is linear and this is continuous, right? Because you know this is the definition, that continuous linear functionals, right? So you already know that this is linear, right? So Tg of f1 plus f2 would be Tg of f1 plus Tg of f2, and Tg of c times f will be c times tg of f. So I mean this is just from the property of integral, that tg of f1 plus f2 is tg of f1 plus tg of f2 and tg of cf equal to c of tg of f. Okay, so this type of thing is there, so it's linear, so it is linear. Now we have to check whether it's continuous or not, right? So for continuity, as I have said that continuity means that mod of f of x should be less than equal to some c times x norm of x with respect to this x, I mean the space which we are concerned with. So here let us take this mod. Okay, so it should, so if you take mod here, so tg of f, right? So if you take mod, you will have mod of fg, okay, x. Now you know that f is in LP and g is in LP prime, right? So okay, so first step would be that you take mod inside, so this would be this, and now you can use the Holder's inequality to get f LP norm and g LQ norm, right? So now this g is something which is fixed, right? So you fixed this g and f is varying. So f is the just like x, f of x, it's just like tg of f. So this is something c, so it is tg of f is less than equal to c times norm of fp. So this is continuous, right? And so this tg is an operator. Okay, so this, so you know the operator norm, right? So do you know the operator norm?
Supremum of mod of t of x for every x whose norm is less than 1.
Exactly, I mean there are multiple ways of defining, so you are saying, what you are saying is correct. So norm of t, if t is some operator from x to y, so it would be mod of tx. Okay, so if you want to be in general, this y is any general normed space, so it will be tx y. Okay, and then you take supremum over x in x, and x is non-zero, or okay, what you were saying, we can write that also, norm x less than equal to 1, like this type of thing. In a similar way, you can take this g in the denominator. So there is another way, is like you divide by x also, right? This type of thing. So I mean if you take g, this g to be less than equal to 1, sorry, this f, right? So this is on the x, this x condition is on x, so you can put the condition. So what you can get is operator norm of tg is less than equal to norm g p prime. Okay, so it's not q, it's p prime. I mean, so sometimes we write q also and sometimes it p prime to denote the conjugate exponent. Okay, so but so far we have denoted it by p prime, so it's gp prime. So we'll have the operator norm of tg is less than equal to g of p prime. Okay, okay. Okay, so I mean here actually you can remove this mod also, and if you further want, you can so remove this x norm x condition also. So there are many equivalent definition. You can just write x not equal to 0 and you can divide by norm x. So there are multiple ways to define this. Okay, so this was about this operator norm. So now okay, so what we have seen in this case, that when you choose this g from LP prime, okay, so when you choose this g from LP prime, using this g, you are defining on operator tg, and this tg is a continuous linear functional defined on LP space. So this tg belong to LP prime, right? This is what we have shown so far, right? So we started off with LP prime and we got this one. Now you can understood that for this tg to be continuous, we need this g to be in LP prime, just because from Holder's inequality we can get a good estimate from where we can deduce the continuity of the operator tg. So you can see that for each LP prime, whatever g you take, this t of g corresponding to this, you have another operator t of g which is in LP prime, right? So this map g going to tg is continuous, right? What this is what this inequality is saying. that the map going from the map G, which is from LP prime to LP prime, right? This is continuous map. So this inclusion, that if you take G from here, you are corresponding to this, you are getting TG. So this G goes to TG. So this inclusion is continuous. Okay, so that's why this is a continuous inclusion. So this is what we have proved so far, right? So did you get what I just said? Yeah? Is this fine?
So,
Yeah.
how to prove the second inequality? Second mode?
This one you are saying?
Yes, sir.
Are you talking about this one?
Yes, sir.
I mean, this is just from the definition. So see what I have obtained so far. This is what I have. Now you take this norm f here, or if you want, you take norm of f to be less than equal to 1. So norm of Tg, by definition, it is mod of Tgf. So it's supremum over f belonging to Lp, and norm Fp less than equal to 1 of
Yes, sir. Got it.
this. You got it? So norm of, so mod of Tg, and from this you know that since this norm Fp is less than equal to 1, so you'll get norm G P prime. Okay. Okay. So so this inequality holds, and now you have this inclusion, that is the map G going to T of G is continuous map, and it's that's it, and it's inclusion. Okay, so for each G you are getting an element which is in LP prime. Now we will try to prove the other way around, that if, so now the next question would be, if I take any LP prime, okay, if I take any linear functional, so LP prime means T is defined from LP to R, and this is continuous. So now if I take any continuous linear functional which is defined on LP, can I get some G? So question would be, can I get G in LP prime such that T is equal to Tg? Can I get that? So that is the question. Okay. Now suppose we are able to prove this, then that would mean that these two sets are actually the same. I mean, sets as a, not as a set, but for, I mean, there is a one-to-one correspondence. So if you have here T, so if you have here LP, and if you have, sorry, LP prime, and if you have LP prime, okay, then you have a one-to-one correspondence between these two sets, that if you choose any T from LP prime, you will get a G such that T is equal to Tg. Conversely, if you choose any G from LP prime, you will get a Tg which is in here, right? Did you get what I just said, or should I repeat? Did you understand this point, what I am saying? So suppose that this is true, suppose this is true, then what it says, that if you have any linear functional here, then corresponding to this linear functional there will exist a function G such that T is equal to Tg. Conversely, what we have proved here, okay, this is what I am saying to assume, that assume this part, that if T belong to LP prime, you will have a G in LP prime such that T is equal to Tg. So from here you can go here. Now I am saying, and this is what we have proved here, that if you take any G from LP prime corresponding to this function G, you can define Tg, and this Tg will belong to this space, right? So you have a one-to-one correspondence, and this is the reason why you denote by P prime, the conjugate exponent. So this is the reason why we use this notation P prime. Okay, is this clear? I mean, you can take a bit time also if you want to digest this.
So,
Hmm?
the third note is the defining the continuous inclusion of LP prime in the dual of LP.
So what is your question? So is this fine? This part? Tell me if you have some doubts, or I'll just proceed further. Is this clear?
Yes, sir.
Okay. Okay, so what I just said is can be proven, okay, but it can be proven for sigma finite measure space, okay, and for p between 1 and infinity and not including infinity, okay. So this is the theorem, what it says. So this is called Rees representation theorem, and what it says that suppose you have this sigma finite measure space, and suppose this p is lying between 1 and infinity, then there will exist a unique. So okay, this is also important, that unique, so that you can get a one-to-one correspondence. So bijectiveness, if you want, you need uniqueness of the element. So there exists a unique function g in LP prime corresponding to this t, okay. So if you start with some t belonging to dual of LP, you will get a g in LP prime such that t and tg are same, okay. In fact, this norm of t, which is obviously equal to tg, will be equal to the LP prime norm of g. So this is called isometry, okay. So this is there now. So I mean, this proves that this LP prime is included inside LP prime, okay. So this is all what I just said. The whole story is written more beautifully, okay. So this is the statement of Rees representation theorem, okay. So this is the conclusion what I conveyed just now, that for sigma finite measure space and for p in 1 infinity, this map g going to tg from LP prime to LP is continuous, bijective and isometry, okay. Isometry means that this norm are equal, okay. Okay. Okay, so this Rees representation theorem is not true for L infinity spaces, okay. So this you can understand by this example. So suppose you have this function, this operator t, which is acting on the space of continuous function. So how is it acting? That t of f is equal to f of 0. So if you take a continuous function, this operator t is evaluating that function at 0, okay. So this is how this operator is defined, okay. So now this t is continuous, right? It's obvious that t of f, okay. So let me just say here that when we are considering this C01 space, we are considering with L infinity norm, okay. So now this mod of tf is equal to f0, and this is in fact less than equal to the supremum norm of f, but okay, I am just taking L infinity norm because L infinity norm for continuous function is same as the supremum norm, okay. And this I have explained many of the times. So so this explains that this function t is continuous. So this t is continuous linear functional on C01. Okay. Now this is, I don't know whether you know this or not. So this is a theorem from functional analysis course. This is Hahn-Banach theorem. So this simply says that if you have a linear function which is defined on some space x, okay, and if you have some other space x tilde, which is, so x is subset of x tilde, okay, and okay, it's this x tilde should have some certain properties, then you can extend this t from x to x tilde. Okay, so this C infinity functions, means this continuous space of continuous function is subset of L infinity function. Okay, and the space are and this is the reason why I took L infinity norm. Okay, so this L infinity, the norm should be same. So when I say x is x tilde, so the norm should be same on both the spaces. Okay, so so this L infinity norm, so we can extend, since t is continuous on C01, I can extend this on L infinity 01, and the extension will also be continuous. This is what this Hahn-Banach theorem says. So suppose you extend this function to this t tilde. Okay, so this t tilde is now a linear functional, continuous linear functional defined for L infinity function. Okay, okay, now extension simply means that t tilde, if you restrict to C01, this will be t. That means if you evaluate t tilde for f which is continuous, now if f is continuous, this will be f of 0. But if f is in L infinity, you cannot make sense of pointwise, right? So if you remember that LP space, when I define the functions, so this LP space does not mean that they are function. These are classes of function, right? We define equivalence relation f g if and only if f is equal to g almost everywhere. So here point wise evaluation does not make sense. So t tilde of f is equal to f0 if f is continuous. Okay, but in general for L infinity function, we don't have the expression, explicit expression of t tilde. We just know that this t tilde is a continuous linear functional on L infinity of 01. Okay, 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 so now I'll show that this t tilde, so okay, so far what we have seen, that LP prime is equal to LP prime, right? So here P is L infinity, so P is infinity, so L infinity prime should be L infinity prime, and for infinity the conjugate exponent is 1, so it should be L1. This is what we expect, right? That this should be true, but I'll prove that this is not true. Okay, so my claim would be claim is that t tilde is not equal to tg for any g in L1 mu. Okay, okay, so let me, so suppose that this is true. Okay, so let me rub this also. If possible, let t is equal to tg for some g belonging to L1. Okay, now let's consider the sequence. Okay, so consider the sequence of functions, so which is given by, so sequence of functions fn, okay, and this fn is defined on 0 1. Okay, so 0 1, so let me just write the definition, that it will be clear. So this is taking 1 minus nx when x is lying between 0 to 1 by n, and at you can clearly see that x equal to 1 by n, it will be 0. So when x belong to 1 by n comma 1, right? Okay, so this is a sequence of functions. Now you can clearly see that fn of 0 is equal to 1, and so it converges to 1, I mean as n goes to infinity. But for any other function, so note that this fn is a continuous function, so this fn is c01, okay? And fn at any point x, if you choose, it will converge to 0. So this fn of x will converge to 0 for all x belonging to 0 comma 1, right? This is clear because you will get an n for which this 1 by n will be less than x, right? And then you will have this 0, okay? So this is just from the expression. So this fn of x goes to 0 for all x. That means that this fn of x converges to 0 almost everywhere, right? Okay, where should I write? Okay, so let me say that this is the first a part, and then, I mean, not part, but this is the first thing, and maybe I can make arrows. So from here I am going here, and again from here I am coming here, okay. So this fn of x goes to 0 almost everywhere. So this t of fn, or t tilde of fn, what is t tilde of fn? Now since this fn is continuous, it is fn of 0, right? And this is 1. So this converts to 1 as n goes to infinity, okay. Now I have assumed that this t tilde, okay, so this t tilde is equal to t of g, okay. So this t tilde of fn is equal to tg of fn, okay, and this tg of fn is nothing but fn times g, okay. Now let us, so with d mu, okay, over 0 1. Now let us look at this fng. So you can see that fng converges to 0 almost everywhere, and the reason being that fn goes to 0 almost everywhere, okay. The second point, what you can see, that this mod of fng is less than equal to mod g, and you know that g is in L1. This is what you started off with. So this g is in L1. So you can use dct, okay. So this is, let's say I'll just put it in the bracket. So now fng converges to 0, so this integral converges to 0 by dct, okay. Now you can clearly see that this and this are contradicting each other, right? This is star and this is star, so star 1, right? So you can clearly see that the star and star 1 contradicts. Therefore what we assumed is not true. Therefore this t tilde is not equal to tg for any g in L1, right? Is this fine? Is this clear? Yeah. Do you have some doubts?
Sir, how is this fn of x converges to 0 for every x in 0 1?
Okay, so okay, if you want I can draw the graph also. From graph also you can see, right? So okay, just let me give just the argument, okay. So now you choose some x, so this is 0, this is 1, you choose some x here, okay. So when x is greater than 1 by n, then this function is taking the value 0, right? So the graph is something like this. So let me draw the graph of fn. So suppose this is 1 by n, then at 1 by n it's 0 and at 0 it is 1, so it would be like this. And then this is the graph of fn, right? Now what you do, you choose some x.
Okay, sir.
You understood?
Okay. Yeah, okay.
Okay. Okay, so now let's move to the next part, which is the reflexive property of this LP spaces. Okay, so now the reflexive property means simply that suppose you have a non-linear space X. Okay, so you know that you can define X prime, the dual of X. So you had this X, from there you defined X prime. Now you can again take the dual of X prime, so you'll have X prime prime, right? So now space X will be called reflexive if this X and X prime are isomorphic, X double prime, sorry. Okay, if they are isomorphic, okay, then we will say that this X is reflexive. Okay, so that's the definition. Now let me just quickly tell you, this is quite easy. Let's suppose if you start off with LP with P lying between 1 and infinity. Okay, so what is LP prime? LP prime is LP, right? LP prime. Now again take a dual. Now LP prime if you want to take, okay, which is nothing but LP prime, what will be this? So see, 1 by P plus 1 by P prime is 1, right? So P prime is conjugate exponent of P, and this P is also conjugate exponent of P prime. Right? So if you take again dual, so this will be conjugate exponent of this P prime, right? So here what you got? You got this P prime is conjugate exponent of P. Now when you again apply the dual, you should get L and the conjugate exponent of P prime, which is nothing but LP, right? When we are dealing with P in 1 infinity. Right? Right? Did you get this point?
Yes, sir.
Now see, these are not reflexive, and the reason being that L1 prime you have calculated above. What it is? It is L infinity, right? L1 prime, but you have seen that this L1 prime is not L1. That this is what I have shown here, right? In this example, right? This is the example which shows that this L infinity prime is not L1. Okay, so this L1 prime, okay, so let me put double, so this is double prime. Okay, so L1 prime is L infinity, and again I am taking prime, so it is L infinity prime, and this is not L1, so this is not reflexive, L1. Similarly, you can show that L infinity is also not reflexive. Okay, what L infinity prime is, so this is space of Redon measures and something like that. Okay, so that is completely, I cannot explain you what it is, but as far as I remember, this is space of Redon measures. Okay, so these two spaces are not reflexive. Okay, let me keep it here. Okay. Now we'll come to this convolution of the functions. Okay, so suppose you have two integrable function on Rn, then you can define this convolution f convoluted with g. So this is called convolution or convolution product as this. So f convolution g is given by integration over whole Rn f of x minus y gy and the integration with respect to y. Okay, so f convolution g at x is equal to this, and so this is the example. Okay, so suppose that fx is given in this way and gx is this. You can try to calculate this f convolution g. Okay, so from the definition what it says that this is, so we are in 0 infinity. Okay, so we are in R, f of x minus y g of y dy. Okay, now you just notice one thing, g of y is 0 when x is in minus infinity 0, right? So instead of integrating on r, I can just integrate on 0 infinity. Correct? I can do that because g of y is 0 when we are in minus infinity 0, and so the product is 0. Okay. Now again notice one thing, that f of x minus y is 0 if this x minus y is negative, right? I mean, from here, this means that if x is less than y or y is greater than x. Okay, and f of x minus y is equal to e raised to the power 3 times x minus y if x minus y is greater than 0 or equal to 0. This is nothing but x is greater than equal to y. Okay, or y is less than equal to x. So since we are integrating with respect to y, so we can integrate 0 to x f of x minus y gy dy, and after x this function is becoming 0, this f is becoming 0. Okay, so that's why we just need to care about 0 to x, right? Now you can write this f of x minus y in this interval is nothing but e raised to the power 3 of x minus y, and g of y is e raised to the power 7 of y. Now you can take x component outside, so you will get e raised to the power 3x, and this e minus 3y and 7y will give you e 4y, and 0 to x dy. Now you can integrate this, so you get e raised to the power 3x by 4, e raised to the power 4y. You can integrate from 0 to x, so you will get e raised to the power 4x minus e raised to the power 0 would be 1. So you get this thing what written. So this is okay. So I just said this. So this is when you are taking x, I mean positive, x is when x is greater than 0, that then only this makes sense, right? This one, otherwise you cannot take this 0x. So for this you have to take x greater than equal to 0. Okay, but if x is less than 0, suppose x is less than equal to 0, then let me write the definition. So this is f convolution g of x, this is equal to f of x minus y g of y dy over r. Now you know that g of y is anyway going to be 0 in minus infinity to 0, so I will just integrate over 0 infinity. Now when x is negative, if x is negative, now you know that y is positive because we are integrating in 0 infinity, so minus y is also negative. So this would imply that x minus y is negative, so this is 0, so this is 0, right? Okay, I was bit fast, so you can tell me if you have some doubt. Are you convinced or do you have some doubts? Tell me if you have some doubts, otherwise I'll proceed.
That's clear.
Okay. Okay, so this was about this just computation. Okay, now I would like to just make one comment here. So you notice that, okay, if you want to do a change of variable here, so suppose I write this as z, okay, then this would be y would become x minus z, right? So this would be x minus z. So if I do some change of variable, now since this y is varying over Rn, this z will also vary over Rn. So this would be over Rn, and you will have f of z and g of x minus z. Right? And the integration would be with respect to z. Right? Because x is in some sense it's fixed. So you'll have this thing. So what is this? This is nothing but g convolution f, right? At x. So f convolution g is same as g convolution f. Okay. So when you try to calculate the convolution, you don't need to bother about the order of this f and g here. Okay. Okay, so that was just a comment. Okay, so this is something again similar to what you have seen. So earlier we dealt with when f belong to LP, g belong to LQ, then where does fg belong? This was our question, right? In the starting. So I solved some problem related to this one. Here the question is that if f is in some space, g is in some space, then where is f convolution g? Okay, so you notice that f convolution g is just a function. It's again coming as a function, and this function of x. So the question would be, where does this f convolution g, does it belong to some LP space? Okay, so this is the answer. The answer is that if f is in L1, okay, so this is one of the, so we have a generalization of this. So let me state this result first. So suppose f is in L1, that means it is integrable over Rn, and g is in LP, then the convolution of f and g would be in LP. So if one of them is in L1, so f convolution g would belong to the space where the other function is lying. Okay, so you forget about, if one of them is L1, you have to consider the space of the second function. So here the second function is in LP, so the convolution is also in LP. Okay, and this is the estimate that f convolution g LP norm is less than equal to L1 norm of f and LP norm of g. Okay, general version of this is, let's suppose if you have PQR satisfying this identity, then if f is in LP and g is in LQ, so again this 1 by R is greater than 1 by P and 1 by Q, right? Again similar to what you have seen initially, right? So if you see this one, this problem, that when f was in LP and g was in LQ, then product was in LR, right? Then here also the same thing, that if f is in LP, g is in LQ, then convolution is in LR. Okay, and this convolution norm is less than equal to LP norm of f and LQ norm of g. Okay, so this one is just for p equal to 1. This is the result. So you can clearly put, if you put p equal to 1, you will get q equal to r. Okay, so now let's talk about this support of convolution of convolution product. So okay, so I gave this example for a purpose. So see, this f, what is the support of f? Support of f is 0, infinity, and support of g is also this, and support of f convolution g is also this. Okay, but in this particular case it is becoming equal, but in general this is true. So in general, so you can see why this sort of result is coming. It's quite interesting to prove this result. So you can see that the support of convolution will be subset of the support of f plus support of g, and this sum is nothing but like this, a plus b is a plus b, where a belong to, so I mean this type of thing. So 1 infinity plus 2 infinity, so it would be 1 infinity, but okay, let me do it in this way. So let's not go to infinity, so it's like 1 2, 2 3 would be 1 would be 3 comma 5, right? Right, it would be like this, right? So I mean, this is the addition. So this is how this defined. So you take element from A, take element from B, and then you add and you set check all the possible elements. So this is how A plus B is defined. Okay, so this support of convolution product will be a subset of the sum of support of F and support of G. In the above example, it is actually it's becoming equal, because if you add this support, so if you add support of F plus support of G, you will get 0 infinity only, and this is equal to the support of F convolution G, but in general it will be a subset. Okay, and you can clearly see how this support is related. So the way I was calculating, I was checking that where this G function is 0, where this F is becoming 0, right? So using that, I was trying to calculate this convolution product. So ultimately, I mean, you can see the proof, so how it goes. So for proof, actually you prove the other way around. So you take complement, you prove that the complement of this is contained in the complement of this. I mean, I think the proof is in this way. So you can check the proof. Okay, so here is one comment, that if F and G has a compact support, that means this is compact, then, and this is a closed subset, right? Okay, and in Rn in this Euclidean space, the sum of compact set is also compact, right? Because I mean, so because this is closed, so sum of closed set is closed and both are bounded, so the sum is bounded. Okay, so in Rn it's true that sum of compact set is compact, so this will be compact, and this is a closed subset of a compact set, so this is also compact. So this is what the result says, that if F and G has compact support, then F convolution G has also compact support. Okay, and the reason is this one. Okay. Okay, now you have this derivative you can also take. Okay, so this is the important thing of convolution. So let me mention it somewhere. So suppose, so what is the benefit, that suppose F is a function which is not differentiable. Okay, so suppose it is very non-smooth, so suppose this is not C1. Okay, but you know some function, let's say you know some function G. Okay, and actually, okay, in the next session I will tell you something, that you have a modifiers. Okay, so you have a good properties with that modifier, so that is useful. So okay, for just now you just look at this one. So suppose G is C1, or suppose G is C infinity in fact. Okay, or whatever order, or let's say just Ck, then this F convolution G, okay, is also Ck. Okay, and this is the benefit of convolution, that if your main function is not smooth, if you convolute it with a smooth function, the resulting function is also smooth. So now you can differentiate this. So, and this derivative F convolution D, so let's talk about just R case, I mean the real case. So dx raised to the power k, or will be equal to F convolution with dk by dxk of G. Okay, so this is how this property is actually useful. Okay, and so this G, if you take a particular type of G, then these things become very useful. Okay, because this is used in approximating the LP functions or in general. Okay, so this G has to be taken properly. I think that I will be telling in the next session. But okay, this is a good property of convolution, that convolving with some smooth function, the resulting function is also smooth. Okay. And this is what more precisely this has been written here, that if F is a continuous real valued function with compact support and G is integrable, then the convolution is also continuous. Okay, so if F is continuous, then the convolution is continuous, and if F is C infinity, then the convolution is also C infinity. Okay. Okay, and the derivative is given in this form. So this is the partial derivative. Okay, and let me tell you what this notation means. So suppose alpha is, so I am just telling you about R2. So alpha is alpha 1, alpha 2. So d of alpha 1, alpha 2, or d of alpha of f will be del alpha 1 x1 del alpha 2 x2 of f. Okay, so I mean, okay, so this is just the partial derivative. Okay, so it says that the partial derivative, mixed partial derivative, I mean, to be more precise, these are mixed. Okay, so if you want to match with this notation, then I can write it in this way. So del alpha 1 by del x1 alpha 1 del alpha 2 by del x2 alpha 2 of f. So such mixed partial derivative also satisfies this property, that d alpha of f convolution g is equal to d alpha of f convolution of g. Okay, okay, I should keep it here, I guess. Okay, so do you have any other doubts, or I mean, is this clear so far? Okay, if this is fine, then we can stop here.